Wi-Fi antennas like this one are perfect if you never leave your house. But the moment you step outside into the real world, everything changes, because if you're building things like Meshtastic networks, experimenting with open-man-a military-style IP mesh radios, or even zero-trust communication stacks dreamed up by some mad genius in Germany, yeah, Reticulum, I see you, antennas stop being accessories and start being the system. They determine how many ones and zeros your network can push and how far those bits can actually go. The utility of these systems cannot be understated, and it's why companies building man-a capabilities are valued in the billions, and why this technology lives almost entirely behind government and enterprise procurement walls. Those solutions work extremely well. They're just completely unrealistic for most civilians, both in cost and accessibility. And right now, sub-gigahertz off-grid radio tech is having a moment. Not because it's a gimmick or some prepper tchotchke, but because it's cheap, open source, decentralized, and frankly, quietly shifting the power away from the communication cartels we've all grown accustomed to back toward the people, which is something this channel fully supports. So today, I'm putting a full lineup of antennas to the test, each one supposedly more powerful, more tactical, and more extreme than the last. I'm ranking them from worst to first to expose what actually works and what doesn't in the free and open unlicensed spectrum. First up is the Muzy 915 whip antenna. It'll run you about $12. And I expect this to perform pretty well because I've used it quite extensively with my LoRa devices. It has good reviews. It is an omnidirectional antenna, so that means the signal is going to propagate evenly in all directions. I do wish there was a little bit more detail around the spec on this. For instance, what the dBi gain is on this, because I guess it's not as important with the current LoRa stacks out there, but with what we're doing with HaLow, we want to make sure that we're under the 4-watt EIRP. So, you know, the antenna gain factors into that. Now, it's probably between 2 and 3 dBi, so we'll just roll with that. But yeah, and I know Simon personally, the guy that runs Muzy Works, and he just lives and breathes this stuff. So I expect good performance out of this relative to the size. You can see the form factor is pretty small here. And I think we're going to be able to get this to punch above its weight class, hopefully. Okay, so right behind me, you can see we have a Haven node on a tripod. So the way I'm going to do this is the roaming node is actually going to be a fixed 915 Muzy Works whip antenna, and it's going to be the base node that we swap out different antennas, because with the directional antennas, it doesn't really make sense to be driving around pointing in one direction. So, but for the first antenna, we have we actually have the Muzy Works 915 whip antenna, which is a pretty standard antenna. It's used for Meshtastic, it's used for LoRa, but can also be used for any Wi-Fi HaLow sub-gigahertz radios as well. So, and then, so we're gonna swap the antenna out here. This is elevated, it's about maybe 6 feet. And for the roaming node, let me show you that. Bruno. For the roaming node, we have another Haven node, and it's fixed to the top of my car. So it's just using one of those GoPro suction cup mounts. And that's also going to be that's going to be a fixed antenna, and we're going to leave that with the 915 standard omnidirectional whip antenna, and then we'll swap out the fixed antenna here. And basically what I'm going to do is I have a script that is going to log GPS coordinates on this node as well as RSSI, which is signal, and that's like raw signal. It's not bandwidth or anything like that, but it's raw signal, which would later then get converted into like bandwidth and stuff like that. So every couple seconds it logs those two things. But the way I run the script on the blue node from within my car is I just go to services, I go to terminal, I log in here real quick, and then I go to Morse scripts, and I put my script in here, and I have this script called roam.sh. And all it does is logs the GPS coordinates every 3 seconds along with RSSI and SNR. So for instance, if I were to run that, I get an output that looks like this. This isn't all the data. It's going to create a big CSV file with all the data, but you can see that it looks at SNR and then it creates a kind of categorical bucket for that. Right now, the two nodes are pretty close to each other, so it's just saying excellent, but that will degrade to good, fair, poor, bad, unusable, etc. as we venture further away from our node. Now, all these antennas can be used on LoRa devices running Meshtastic, MeshCore, or even Reticulum nodes. But for this video, I'm using them with Wi-Fi HaLow 802.11ah. Everything you're seeing is running on a Haven-style node, essentially a small open-source off-grid router built around a Raspberry Pi and a HaLow radio, designed specifically for portable mesh networking. It runs an open project called b.a.t.m.a.n, which uses b.a.t.m.a.n layer 2 mesh, the same class of networking used in real field and tactical deployments, and it pairs extremely well with tools like ATAC. The key difference versus LoRa is bandwidth. Instead of pushing kilobits per second, Wi-Fi HaLow gives you megabits with full IP networking under the hood. So we're going to be able to know where we are relative to the base node and then what kind of signal we're getting. And I'm going to do a lap, kind of perimeter lap. I think it's 4 miles long and like 2 miles wide. So I expect to lose signal pretty quickly, but I want to drive around and see what it looks like on a map when we're done with that. So that's our objective. Okay, so I actually ran 2 tests for each antenna. The first one was in my neighborhood. So this is the Muzy data in my neighborhood, and you can see that if I zoom in here, these are all data points. And then the color scale here tells us the signal. And so I started out right here at my house, and then I drove around with one of the nodes on my car, and it gave us this projection here. For scale, from here to here is only 1,200 feet. So, not that much distance actually. And that's why I wanted to do another test in a more open area, because this base node also was inside my house, and my house is a cement brick house, so there's immediately it needs to penetrate that, which is hard to do. HaLow can do it, but it's just it's not giving it the best sort of shot at having a lot of distance. So I wasn't really a big fan of that test, but still interesting to see what the data kind of looks like here as you go further out. The signal becomes poor. I'm still getting some decent distance around my neighborhood, so that's cool to see. But let's look at the data out in the remote area. So I'm going to turn this on, and I'm going to come over here. So, so I think this one's a little bit more interesting. In the corner there is where I had the base, like the stationary node. And this node was sporting again, in this example, it's the Muzy antenna. And then I drove out in this direction, and then I drove up in this direction. And the reason I wanted to go in a right angle is because when I use the directionals are going to point in this direction. And we're going to see how that differs from over here. And we can see that, it's pretty uniform, right? You have the good, you have the, I think that's the excellent. Yeah, you have the excellent here. You have the good here. You have the fair here. So it's that donut shape that we expect. And then real quick for scale, and this is where it gets more interesting. From here to here is actually 2.5 miles. So if we're getting, if our signal cut off at about the midway point there, then we're technically getting 1.25 miles with Wi-Fi HaLow, which is really exciting. And this wasn't perfect line of sight, but it was pretty close. It was basically farms. So for the most part, it was good line of sight. But I will say, going in this direction, there were quite a few berms that kind of would have obstructed line of sight, but you still see the signals pretty strong there. So anyways, I thought this data was pretty interesting. Okay, now escalating a bit here, we have the Meshtac flat top version. There's two versions of this. One is a pointed top, one's flat. 915 antenna, a gooseneck antenna, which means we can do this. And it's just a little bit better, more rugged structure here. This guy will run you $35, so a little bit more expensive. Still tuned to the same 915 center frequency that we want. Probably honestly inside very similar to the Muzy Works antenna, but you get all metal kind of housing here. Just much more rugged. So this guy is an omnidirectional antenna. It has a 4 dBi gain. SMA male connector, good for LoRa and HaLow, and it comes to us from Rockland. It has some pretty solid reviews. Yeah, lots of specs around this antenna, which I like to see, and I know the nerds among us appreciate that. But also just looks super nice, right? Like a couple of these on a mobile radio. Kind of gives it really that sort of military aesthetic that we're going for out in the field, but a little bit pricier on the other hand. So let's see how this guy fares.
So one of the things the script is kind of showing me, which wasn't exactly intuitive, was the biggest factor just seems to be the distance. I know obstacles are important and reflections important and multipath and all that stuff, but and you do see some volatility, but the biggest sort of common denominator in terms of the trend of your signal is really just distance. I've been surprised where like there might be houses in the way, there might be trees, there might be outright berms, which is very dense material and stuff like that, but it's really just been the distance has been the biggest factor.
Okay, so next up is the Meshtac data. Let's take a look at that. So this is what it looked like in my neighborhood. Let me zoom in. So you can see the Meshtac wasn't quite as successful as the Muzy, interestingly. There's more examples of poor, unusable signal, at least in my neighborhood. And then if we pull it out to the open fields there, the signal didn't go quite as far as it did with the Muzy, and there was no extremely strong signal. So it immediately just started at excellent, and then good, and then fair, poor, bad, etc. But it wasn't that different than the Muzy data, right? If I superimpose that, here, let me zoom out a little bit. If I put the Muzy data back on, the Muzy did a little bit better over here, but it wasn't that dramatic. So anyways, that's the Meshtac antenna. Okay, now venturing off the beaten path a little bit. And I'm pretty excited about this because this is a more advanced antenna than what I'm typically using out in the field. This is the Sig Hunter from Taoglass. Now, we've run into Taoglass before. They created the passive GPS and cellular antennas for the Walter IoT device that we had covered in the past. They have a very good reputation. They provide more information on their antennas in terms of testing and specs than any other vendor I've seen. There is a full data sheet. But what's interesting about this antenna, in addition to its sort of hatchet form factor here, is that this is a directional antenna. So the idea with that is that instead of the omnidirectional with the signal propagating evenly like a donut in all directions, this is going to have I think it's like a 45-degree angle direction. So you're going to get a more concentrated beam in the direction of the blade. You'll still get signal like perpendicular and behind, but it just won't be as strong as directly in front of. And there's other factors around like the exact propagation pattern and stuff like that. But the point is this is a directional antenna, but it's also still fairly sort of mobile form factor here. We have an SMA male connector here. But what's interesting also is I don't know if I would call that a gooseneck, but it's certainly flexible, and it kind of remembers the shape that you put it in, so you could point it and adjust it as needed on the fly. This guy ran us $48, so a little bit more expensive as well, but very unique sort of form factor here. So this has a dBi gain of 4, which is pretty strong, and the range is from 860 to 928, which is pretty good for us because we are going to be projecting off of 915. So that should work for us. But yeah, this is a really cool looking antenna, and I have high hopes, and I'm very curious how this fares relative to the more stock omnidirectional antennas.
Game recognizes game. Looks like a Yagi. So I'm actually really surprised about the Sig Hunter because I'm now going in a direction that's at a 90-degree angle to the direction, the propagation of the signal, and I'm pretty far out, but I'm still getting a decent signal here. So not quite what I would expect. It's a little bit more forgiving in terms of going in other directions than I would have expected. So that's kind of cool to see. Okay, so now let's look at the Sig Hunter. So this is the first directional antenna that we have. So if I pull that up over here, so this is the neighborhood test. And I actually thought this was pretty interesting. Sorry, let me just get this going here. So I pointed the antenna. In this direction. And you can see that the signal propagates that way. Like even all the way out here, we get some instances of fare all the way out here. So I was pretty impressed with that, with the Sig Hunter. So that's the first directional antenna. And it actually did pretty good over to the left here as well. We see a lot of greens here. So anyways, with these tests, there's lots of like random variables and things like that. But the Sig Hunter in the urban setting was pretty impressive. Now the Sig Hunter in the rural setting, let's take a look at this here, was not that different than the Omnis, to be perfectly honest. So I don't know exactly what to attribute that to, but it was pointing in this direction because every time I used a directional, I pointed it in that direction. But you can see, it still kind of radiates in what seems to be, that donut shape that we expect. So I would have expected more signal in this direction with the Sig Hunter than I actually got. So I don't know, that could be user error. It could be, I don't know, a placement or something like that. But it just wasn't as directional as I would have expected.
Okay, we have a Yagi antenna from Alpha Networks. They make quite a few pieces of hardware in this space, including HaLow chips themselves. We got this from Rockland. It ran $65, so more expensive. Definitely not very discreet. I'm going to take a bit more to mount this. To mount it, you have these sort of like U-straps here, so you can put it on any sort of pole that you have. I put it on a tripod mount, seemed to work fine. But again, this is a directional antenna. This is a 12 dBi antenna. It's tuned to 915, which is what we want. But again, it's going to be propagating its radiation in a particular direction. The connector, this is a N female connector. But again, if you have that universal adapter kit, you can convert this to SMA pretty easily. I also got a cable to use kind of as an extension. But yeah, I'm really excited about this one. Yagis have been around for quite a while in terms of directionals. And I'm very curious what this gives us in terms of range.
So this is pretty interesting. I'm pretty far down, and the Yagi started getting some excellence out of nowhere, which no other antenna has done. So obviously it's a directional, so you'd expect that to some extent, but kind of cool to see it show up in our script here.
So the Yagi in my neighborhood looked like this, and let me zoom in. So again, it was pointed in this direction like that, and you can see that's kind of how it plays out. We get some, yeah, some fares. We get some fares pretty far out here, and then we get poors, and then we get bads. It did decent in this direction, did decent in this spot here where others struggled. But honestly, I don't know. For how big and clunky it is and the dBi gain, it didn't really give me the range I would have expected. I would have expected this whole corridor here to be lit up as a strong signal or a good signal. And that's not really what we expected. But let's go out to the rural setting here. So again, the signal was pointed this direction, and you do see that it carries excellent quite a bit further than any of the other ones. But then it quickly drops off to good, and then it goes to, fair, and then poor. And I don't know, it just, again, the directionals aren't as directional as I would have expected. You can kind of see it here, right? This goes out further, and then this goes out further. So it's definitely directional, but I don't know, it's not as dramatic as I would have expected. So I don't know if that's user error. I don't know exactly what that is. But for me, that big sort of bulky antenna wasn't really justified so much. And the directionality component wasn't really justified so much. I would have been kind of just as good off just using an omnidirectional antenna. So I don't know. One of the lessons was the directionals weren't as directional as I would have expected. Now, for these military style builds, you might be wondering where I'm getting these pricing figures. And yeah, some of them sound exaggerated. They're not. One of you reached out, a viewer with access to defense procurement systems, and helped me sanity check official pricing across dozens of devices in this space. Think the usual players: persistent class gear, L3 Harris type systems, Silvus Man-8 radios. I'm not going to disclose specific SKUs or line items here, but what we saw were radios pushing well into 5 figures, mobile Man-8 systems comfortably over 10 grand, and even something as basic as a 7 amp hour battery costing around $500. Meanwhile, you can buy 2 off-the-shelf 21700 Moly cells, get more capacity, about 9 amp hours, and spend just about 20 bucks. And that gap right there, that's why I believe this topic matters, because as taxpayers, we all have a stake in ensuring transparency, particularly when we're talking about systems that cost this much. Which brings us to the final antenna in our repertoire here, the Yogurt Cup sub-gigahertz tactical antenna, which you can buy from 5-4 Communications. But this is actually designed by an individual. I don't know his name, but I have his Instagram account. Heads down, comms up. So you literally have to DM him on Instagram if you want this. The original variant is not 900 megahertz. The original variant is much lower. It's between 100 and 450 megahertz. But he was able to build a sort of LoRa HaLow version for me. And I have no idea what's inside this thing or how it works. You can see it has an entirely different form factor than these other antennas. But it definitely also has that military aesthetic. Anyways, yeah, you have a thread here that allows you to put a gooseneck on it like so. But again, that's just for, setting it up and configuring it. But for actually attaching your radio, it has this unique connector called a BNC connector. And the idea of that is that it is a quick attach, detach. Let me show you how that works. And it comes with a cable, but basically all you have to do is go like that and it's in. So pretty easy to attach and detach relative to the SMA connectors that we're a little bit more familiar with here. And then on the other side here, you have another BNC. But what I did was I just put an adapter in here that goes to SMA so that this could plug right into our Haven node. One thing I would recommend is getting a universal adapter kit like this. Basically has every sort of conversion form factor for these antennas, and then you know that you'll always have the piece that you need to get your antenna working. This has helped me out quite a bit. Anyways, so it looks like this antenna here is a 3 dBi gain. It is omnidirectional. But the thing about this is it's got a lot of positive reviews in the field. So I'm pretty hopeful about this. And I gotta say, it just looks awesome.
So I'm pretty impressed with the yogurt cup antenna in both directions. It seems to have a stronger signal than really the rest of the antennas. So I'm not really sure what the magic sauce is there, but definitely going to keep it as a daily driver type antenna. I just got to find a nice way to connect it to the Haven node because it has that sort of special connector. But yeah, it was getting a pretty good signal pretty far out.
Okay, let's take a look at the yogurt cup in the neighborhood. So I'm going to zoom over here and let's take a look at this. So if we zoom in, so the yogurt cup did pretty well. You know, it got pretty far down here. But again, with the obstruction of the houses, didn't do so well. Didn't make it out here so much. So one of the interesting things about the yogurt cup is, though, that it did report extremely strong when I was close to it. A lot of the antennas didn't, which was interesting, but the yogurt cup does. So I kind of liked that about the yogurt cup. But, you know, not a huge night and day. I guess you could say, you know, it did pretty good with this patch here. So, you know, solid showing, but not groundbreaking, so to speak. But let's look at the yogurt cup in the rural settings. So let's zoom in. And this I did think was kind of interesting because, I zoom in a little bit. It got, again, a lot of, it got a good number of those extremely strong signals when I was close to it that I didn't see with a lot of the other antennas. And then it got excellent. Again, yogurt was omnidirectional, so we would expect that even propagation, fair. And I would say the yogurt went further than the Muzy, actually, right? Because the Muzy, we put the Muzy at like about halfway, but the yogurt got more than halfway. And again, this to this is 2.5 miles. So this puts us at like, what, 1.8 maybe? Which again is just super impressive for these Wi-Fi HaLow mesh setups. So that is the yogurt cup. One thing that really stood out to me doing all these tests is how little antennas have actually changed. Dipoles, whips, Yagis. These designs are decades old, and for a long time, the only real lever we had was more gain or better placement. But that's starting to change. A traditional whip or dipole is manually tuned on a jig. You're bending metal, trimming length, chasing resonance, which means there's always tolerance. It can only be so precise. But newer designs, especially PCB printed antennas, flip that completely. They are geometrically exact, mass-produced with extreme consistency, perfectly tuned every single time. And that opens the door to something more interesting than just adding more gain. See, a dipole has a theoretical best case when it's perfectly parallel to the receiving antenna, and a theoretical null when it's tilted on its axis. In the real world, we still get signal mostly because reflections bail us out. But those same reflections are also what cause multipath fading, signals arriving out of phase and canceling each other out. That's where some newer research gets really compelling. Now, Trey over at Morose X has sent over some prototyping antennas he's rolling out, and literature from some recent studies suggesting that for man-A environments, especially non-line of sight, moving nodes, urban clutter, trees, vehicles, that circular polarization starts solving problems that raw gain never could. Circularly polarized antennas don't care about orientation the same way linear antennas do. And when signals reflect, their polarization flips. The trick is to use both, a right-hand circular antenna and a left-hand circular antenna, and then let MIMO treat those different polarization paths as diversity instead of interference. Instead of fighting multipath, you leverage it. Now, to be clear, these specific antennas aren't sub-gigahertz, so I can't meaningfully test them in this video, and today MIMO isn't really implemented in HaLow or LoRa hardware the way it is in traditional Wi-Fi, but it is in the spec, and this exact approach is already used in the FPV world to get insanely reliable links in chaotic RF environments. I believe this is where off-grid communications are headed next. Not just more power, but smarter antennas that understand polarization, multipath, and motion, enabling beyond line of sight, non-line of sight, and more signal than we've ever seen before. At least that's the hope. To find out just how deep the rabbit hole goes, click here. Thanks.